Okay. So next up in the performance extravaganza this morning is Jay Foad. Jay's been with Dyalog for 3.5 years now. And after sitting politely in the design meetings for the first year or so, year and a half, with an occasional frown on his face, he's now really started telling us his opinion. And he's working on some very interesting projects. He's here to tell us today about one of them, which is a project to reduce interpreter overhead. Jay.
Thank you. Is this on? Yep, good. Does this work? Yes. Right, so for those of you who I haven't met, I'm Jay Foad. As Morten says, I've been at Dyalog for a few years, and before that, my background was in more traditional compilers. So I worked on various C compiler systems and also on some Java just-in-time compiler technology and virtual machines and things like that. So I'm quite interested in the performance of virtual machines and how you can start compiling them in order to improve the performance. And I'd like to try and start bringing some of that into APL. I'm talking today about this particular project that I've been working on for a couple of years. It's kind of experimental, but getting to the stage where we're getting some real results on particular kinds of code. So it's at a stage where we can do a beta release of it in version 14. I should stress before I start that as it's experimental, it won't be enabled by default out of the box. Version 14 will not be using this technology, but it's available there for you to play with if you're interested. The project has gone through various different names. At first I called it an optimization project because I didn't want to call it a compiler, and then it turned into a compiler, so I thought, well, why not just call it a compiler? It's also sometimes referred to as a new parser for Dyalog, and as Morten said, it's targeted firmly at reducing the interpreter overhead, so I think that's how it's billed in the program. There are really two goals of this project. The first one, as we said, is to reduce interpreter overhead. That's the direct reason for introducing this compiler technology, but it also serves as a way to enable us to start thinking about more sophisticated optimizations in the future. So what we hope to go on to do over the next few years is to start implementing some more kind of high-level optimizations on the code that you write so that it can be executed more efficiently. And I'll talk a little bit about our ideas for that later on. So the Dyalog APL is interpreted and always has been, and this has served us well for a long time. Somebody last night asked me to explain a little bit about how the interpreter works, and that seemed like rather a large subject, but for the purposes of this talk, I would like to say a little bit about how it currently works, and in particular, what happens when you define a function, and then later on, what happens when you execute that function. So the current system is that when you define a function, we say that it is fixed. So if you've entered a function in the editor and you hit escape, that fixes the function. Or if you use quadfx to dynamically generate some code, and when you run quadfx, that fixes a function. And at that time, we do what we call tokenization. So each line of APL that you've written is converted into a fairly compact token representation. And to a first approximation, it uses 1 byte for each token, and a byte represents either a name that you've written in the code, or a constant, like a number or a string, or it can represent any of the individual symbols, so the primitive function glyphs, or parentheses, new lines, any kind of symbol that appears on the line. So there is that little bit of work that occurs at fixed time, but it's a very, very direct translation of what you wrote. Nothing sort of sophisticated goes on at that time. And in fact, it's such a direct translation that when you bring the function back up in the editor, or if you get an error in your code and we want to display a line of code, it actually takes the tokens and turns that straight back into the text, which is more or less as you wrote it when you started. Then when you come to execute a line of APL, it runs through the parser, and it's the parser's job to worry about John was talking a minute ago about all these binding strengths, about how operators bind to their operands tightly and functions bind slightly less tightly, and you can use parentheses to override it. The parser's job is to sort all that stuff out. So every time you execute a line of APL, the parser starts at the right-hand side, picks up a token and says, right, what have we got? Is it an array, a function, an operator, a parenthesis, or any of the sort of special syntax? And in particular, if you execute the same line of APL multiple times, so if you have a for loop and the line inside it is executed 1,000,000 times, every time the parser comes to that line, it starts again. It's got a goldfish memory, starts at the right-hand side and says, right, what have we got? Have we got an array? Have we got a number? Have we got a function? And proceeds from right to left, parsing the code and executing it as it goes. And so for the execution part of that, every time it's got a primitive function in its hand and it's found an argument and optionally a right argument and optionally a left argument, it then calls dedicated code to execute that particular primitive function. So APL is an array language, and if you use it to the full and you always have nice large arrays of data and you always operate on them in parallel, then what you find is that most of the time is spent inside the implementation of each primitive function doing multiplication on arrays of, 100, 1,000,000 elements, whatever it is. And that's great, and that's one of the reasons why the fact that APL is interpreted has not been as much of a problem as it would be in other programming languages. But sometimes you don't have large arrays, or you can't find a way to express your algorithm that means that the primitives are applied to the whole array. You need to chop it up and do little bits here and there in sequence. So that is where the interpreter overhead becomes a problem. If the individual primitive function, the primitives themselves are highly optimized for large data. That's the kind of thing that Roger does every day. They've traditionally been very well optimized, and we continue to do that. But if you do not have enough data to keep them busy, if you're just operating on scalars or small arrays all the time, then the proportion of time that is spent in those primitives is relatively low. And what you find is that the time spent in the parser doing all this kind of bookkeeping of trying to understand the structure of the APL language takes a significant amount of time and slows things down more than it should. I'm just going to show a couple of very simple examples of the, uber simple examples of the kind of code we're going to look at. The first one is a loop function that does absolutely nothing useful. You can give it an argument of, say, 100, and it will loop 100 times and then return 0. The only interesting point about it is that all the primitive operations in there are as trivial as you could possibly imagine. You test whether the argument is 0. The guard is another test to see whether the result of that comparison is 0 or 1. You subtract 1 from an integer, and there's a recursive call on the dfn, which is already pretty well optimized. So there is virtually no work for the primitives to do. So the runtime of that example is completely dominated by the parsing time. When I run that on my laptop, I get about 2.5 million iterations of that loop per second, which is, it sounds okay. But if you wrote it in C or C# or any compiled language, you could expect to get a factor of 100, maybe even 1,000 faster than that. So there is certainly, in cases like this, there is a lot of room for improvement. And that's good news, isn't it? There's plenty of work to do. And this mean here just computes the mean or average of typically a vector. This is a function that I'll just show you a few times as we go through. If you've been in the morning's talks, you'll know exactly what this function here is. It's tally. It's the cool new replacement for shape or row, if you want to know the length of an array along the first dimension. So I'm going to explain a little bit about what kind of overheads the parser incurs. And there are really two things here. One is that One is what I call just the unavoidable consequences of the fact that we're using an interpreter. That means that it has to make these decisions afresh. Every time you execute an expression, it has to work out what to do before it actually gets around to calling the primitive functions that do the real work. But the other thing is that there are a bunch of overheads that are kind of unfair in that they punish you for using features of the language. There are cases where the parser has a difficult job to parse something. It has to go and allocate some memory to hold some state, or things like that, that mean that features of the language you ought to be able to use with no penalty actually end up costing a little bit, and it can be measurable. So this example, the mean example here, when I started writing APL, I thought that was a bit weird because you've got a divide in the middle and you've got an expression on each side and you've written parentheses around one side and not around the other, and that looked asymmetrical to me. So if I'd been writing that, I would have put parentheses around the right-hand side. And if you got completely obsessed, you could put parentheses all over the place. And what you'll find is that if you do write that, it works just fine, but it runs an awful lot slower than the original version. And that's kind of sad, because it would be nice if the programmer could put the parentheses in wherever he likes to, you know, for clarity, and not be penalized for it. I think that's beautiful. What's wrong with it? I missed some out, actually. You can put them around the these functions as well. Yeah. Another thing in the same vein, if you put lots of comments in your functions, or leave lots of blank lines, again, for clarity, that does actually slow it down. Now, to be fair, in version, I think probably in 13.2, we did a bit of work on this, and it's not as bad as it was, but it still makes a measurable difference if you leave blank lines in your functions, which again is quite sad. It would be nice to be able to put blank lines and comments in wherever you like and not worry about it. Another one, most of this talk is going to be focusing on dfns. And this is something particular about dfns. You're encouraged to write dfns like this with lots of, you know, local assignments. All the names you assign to are implicitly localized. And that's a very nice model to work with. But unfortunately, again, that's something that takes a little bit of parsing time up. So if you think that it makes your function, you think it's a nice way to lay it out like this, break it up into small units, name the parts of the computation. Seems like a good idea. This is actually, again, incurs a significant overhead. Each time you assign to a fresh local name, it has to go away and, as I say, it implicitly localizes it. So at that point, it goes away and remembers the old value and pushes some stuff on the stack. So again, that's a shame. Have I got any more? There are more examples of these things. If you use square brackets, it's pretty much the same thing as square brackets for indexing. You get the same problem as parentheses in that it takes a little bit of time to parse them. So there are cases where if you do your indexing in a different way, maybe by using pick or by the squad indexing, it'll go faster. And again, that's a shame. And here's one I bet you didn't know. If you write plus reduce 1, 2, 3, it takes the parser a little bit of time to take the plus and the slash and bind them together into the single function plus reduce. And you can actually make that go faster today by naming the derived function plus reduce. If you do sum gets plus reduce, you know, somewhere globally, and then write sum 1, 2, 3, it'll go slightly faster than doing plus reduce of 1, 2, 3. And again, that's crazy. That's sort of, to me, coming from a compiled language background, that's kind of indefensible. So with the compiler project, what I hope to do, and hope I can demonstrate, is that it will reduce the general unavoidable interpreter overhead. It should all run more efficiently. And in particular, it will eliminate most or all of these kind of unfair penalties. Now, how do we do this? The general strategy is to move much of the work of parsing away from runtime and to do it all at fixed time when a function is defined. So with the compiler that I'm working on, you can, well, you have a choice over exactly when the compiler is invoked, but one mode of using it is that every time a function is fixed, the compiler will run. It'll run quickly and quietly in the background. You don't really need to know it's there unless you want to. And at the point where you fix a whole function, it will analyze the whole function, not just individual lines of APL, but the whole thing. And it will work out the parse tree, effectively, for the entire function, and do that work ahead of time. And then it saves the results of that, and I'll show you how it does that and how it then uses that to execute the function more quickly. There's a bit of a problem with this, which is that it's kind of well known that you can't parse APL statically. APL has always been parsed and executed at the same time, and there are good reasons for this. If you see a line of APL that looks like that, you have no idea what it means, because you don't, if you're looking at that statically without all the information about the values of variables in the environment, you don't know what it means. A, B, and C, because you don't know what the values of A, B, and C are. They could be arrays, they could be functions. In Dyalog, they could even be named operators. So they could all be arrays, in which case that's strand notation, and you get a vector. B could be a function, and A and C are its two arguments, in which case it's a dyadic application of a function. A and B could both be functions, in which case it's apply one function monadically and then the second function to the result of that. B could even be a named operator, so you get a plus reduction. Or B could be a dyadic operator, and A and C are functions. And I meant to put an extra one on the end, which is to say it could be a train of three functions. So, fortunately, well, there are a couple of saving graces here. One is that it's actually rare in practice that you see a line that just looks like that without enough context to know what's going on. And especially if you're writing small functional defns, which is what we're trying to encourage, the use of any names like this that aren't defined locally is relatively rare. So because the compiler operates on an entire function at a time, if it could see on the lines above that you'd assign to A, B, and C, then it's got enough context to know what's going on. It can see whether they're arrays or functions. And the other thing is that because this compiler's embedded in the existing Dyalog interpreter, it always has the luxury of just giving up and saying, sorry, I don't know, I can't parse this, I don't know what to do with it. And again, for the most part, that will happen transparently behind the scenes. You don't even need to know if you don't want to, and it will simply fall back to executing your function using the existing parser. So what does the compiler do? Fundamentally, it takes a single function. This is based on the mean example here, where I've named the sum of the argument and the number of items in the argument, and produces a tree. If there are any graph theorists in the audience, I should say it's a directed acyclic graph, but I'll call it a tree. And this tree diagram is a diagrammatic representation of what it builds up as it does the parsing. Each of these little lines of three boxes represents a function in the middle being applied to either one or two arguments. So the result of the entire function was this division, and this bit over here represents sum, this bit over here represents num. Sum itself was the application of a function, which is, again, I'm using three boxes to represent a derived function, plus reduce. And the argument omega was used in two places, so it appears once in the tree, but there are two arrows pointing to it. So that's the kind of structure that it builds up internally. And that's important because that's what lets you do these slightly higher level analyses of the code. Again, I'll talk about that a little bit more later. So first builds up a parse tree. At that point, it has the opportunity to do, clever stuff happens there. And then instead of keeping that tree, what it does, it turns it into a compact bytecode. you're not expected to read and understand this. It's all it is a compact representation of what you need to do to execute the function. And you could say, well, that's not so very different from what we did in the first place. We had tokens. That was a compact representation of the line of APL. But when you're trying to parse the tokens, you're still effectively parsing the whole of the APL language, whereas this is very much a series of simple instructions, mostly saying, pick up this value from here, put it there, apply this function, put the result there, put this value here. It's the whole design of this bytecode language is to make it efficient to execute it. And in particular, all of the things that I said were unfair penalties, so having things like local names in your function. By the time you get to this representation, all the local names have disappeared. I've written them on there just for decoration, but in the internal representation, the local names have been thrown away. The parentheses aren't explicitly represented in there, the blank lines and comments, all that stuff has been thrown away and no longer makes any difference. So you can put as many of them in as you like, and it will make no difference to the compiler. So I said that the bytecode is designed to be executed efficiently. Does it work? Well, yes. Here's a few examples that I ran earlier. The mean expression here, mean of 1, 2, 3, 4, this is the function that I showed where it has local names for sum and num. And this kind of, it gives the compiler a bit of an advantage because the interpreted version of that is noticeably slow. So these are kind of typical speed-ups that you see running simple defns on small arguments. In a favorable case, you might get up to about a factor of 2.5. Root, I haven't showed you. It's a defn that gives you the nth root of a number where n is the left argument, and if you don't give a left argument, it gives you the square root. So root 10 is pretty much doing omega to the power of the reciprocal of 2. It's very, very simple. And even on something like that, although the time we're measuring is very small, you tend to see about a factor of 1.4 or 1.5. Easter down the bottom is a function from the defns workspace, which you may or may not have seen. It calculates the date of Easter for a specified year. And I'll show you the code for that later. The only interesting thing about that is, although I'm talking about small defns, Easter is actually quite large. Well, there's a lot going on in it. It's about 15 or 20 lines of code and 40 or 50 primitive functions. So most of the examples I'm showing are on very, very small bits of code, but there are examples where it can scale up to sizable chunks of code. Now, I think I mentioned that there were various limitations on what the compiler can handle, and it's free to give up at any time if it sees something in your code that it is unable to analyze. So these are a few of the examples of the kind of things that it currently gives up on. Now, some of these are kind of fundamental restrictions on the compiler technology, and I'll try and explain why the restrictions are there. Some of them are simply things that we haven't put the effort into supporting yet, and so gradually this list should shrink, but there will still be things you should know about that the compiler cannot analyze. And this is one of those. This is the most fundamental restriction at the moment, is you cannot refer to any global names or even semi-global names from your function. This is really why we say that concentrating on a pure functional style where the only computation you do is on the arguments you've given, you do some work on them and return a result. The reason for that as it relates to the compiler project, when the compiler comes to analyze your function, this is just one that I chose from the defns workspace called compidn, which is something to do with computing date numbers or something. Pardon? International Day numbers. But the first thing it does is to call another function in the defns workspace called days. And the problem with this is that the compiler works on one function at a time in isolation. When it's analysing this function, it has no idea what days it is. In particular, it doesn't know if it's a function or an array or an operator. It doesn't even know if it's going to be defined at all when you come to run this code. And at that point, it gives up. So, as I say, that was the most fundamental restriction, and that's why, for this kind of technology, it's a good idea to write in a functional style. Other limitations, you may not be surprised to hear that if you use execute in your code, again, the compiler really doesn't have the ability to analyze what code you're going to run there. So again, it just gives up straight away. Another one is namespace reference syntax. So in the compiler project, I haven't thought a lot about namespaces yet. The namespace reference dot is a difficult one to analyze for much the same reason. This is a function that takes a namespace as an argument and then pulls out something called f from that namespace, which you might imagine is a function, and something called x, which you might imagine is the argument. But the compiler doesn't know that for sure. It can't analyze that because it has no idea what namespace you're going to give it at runtime. So at some point, we'll have to think about this a bit more. For the moment, it just gives up if it sees a namespace reference dot. And here's an example of something that we simply haven't got around to implementing yet. There's no fundamental barrier to supporting selective assignment in the compiler, but it wasn't top of the list and it seems like a lot of work, so it's not there yet. So something I should have perhaps mentioned when we're talking about the kind of performance gains that you get from this at the moment. If you run these kinds of expressions in the existing interpreter, and then run a profiler on the interpreter to work out where the interpreter itself is spending its time, you find for this kind of scalary code that it spends about half its time doing parsing work and about half its time in the individual primitive functions themselves. So that's really why the speed-ups that you get from trying to eliminate the parsing work, they tend to sort of max out around about a factor of 2, give or take. The interesting thing about that is that after you've done that work, you then find out that it's spending, 10% doing the bytecode execution and 80 or 90% of its time in the primitive functions. And that, I see that as an opportunity. That actually opens up more opportunities for then going back and looking at the primitive functions and, in particular, specializing the primitive functions so that they are more efficient on scalars and small values. So again, that's a separate project really, but this kind of opens the doors to that work. So I showed you a few limitations on what kind of code you can write, but in practice, those limitations aren't too bad. So I just want to demonstrate that there are still some sizable, useful chunks of code that you can write, which the compiler is perfectly happy with. This is the Easter function that I was talking about before. As I say, it's got 50-odd scalar primitive functions going on in there. It's got a bit of a inner product and a mix. And it's very simple regular code, which is good for the compiler. In general, I keep saying that it's targeted at small functional functions, and the reason for that really is if you write small chunks of code, there's much less chance that you will run into one of these limitations. So it's good to try and divide the work up into smallish chunks. Another function, again, picked at random from the tradfns workspace. The interesting thing about this is that I said that you could not refer to global names, so you were not allowed in a top-level function to call another function. But that's not quite as bad as it sounds, because using tradfns, you can have nested tradfns within tradfns. And when the compiler comes along, I said it compiles a function at a time. I was actually being a bit sloppy with its terminology, with my terminology. What it actually does is compiles an entire top-level, what we call a tradfn capsule, which is the d function and any other d functions that are nested within it. So in this particular case, you have 2 local helper functions defined, and the top level code decides which of those two functions to call. So that is fine. If you're happy structuring your code in that way, that gives you a way of breaking it down into smaller functions. And in this case, because the compiler can see the whole thing at once, it's entirely happy compiling that. I should say a little bit about the user interface. There isn't much of one. It would be really nice if there was none at all, if we could release this and you wouldn't even know it was there and everything would just run faster. That's a bit of a holy grail. Because it's still experimental, we're not at that stage yet. What we have at the moment, just for testing purposes, is an iBeam interface to control whether the compiler kicks in automatically. As I say, you can enable it so that every single time you fix a function, it will run in the background and try to compile it without asking you. Yes? The index origin. The question was, does the index origin make a difference? No. It turns out that the compiler does not care about that. The individual primitive functions do care about it, but yeah, it's all handled in the individual primitives. The compiler doesn't care. Yeah, so the iBeam interface to the compiler, you can also ask it on demand to compile particular functions, or to, if you didn't like the compiled version, you can ask it to throw that away again, and you can query whether functions were compiled successfully. And there's a limited form of diagnostics. That's something that we probably need to improve. If you have the question, I tried to compile this function and the compiler didn't like it, it would be nice to get some really useful feedback about why it didn't like it and what you need to change. That's work in progress at the moment. So all of that really was talking about the first goal that we had of reducing the interpreter overhead. The second part of it, so what I've talked about so far is implemented. I've shown some results and it's fairly stable. The second part of it is more future work that we've started thinking about. And this was the fact that the compiler technology enables us to start thinking about high-level optimisations on the code. And really, this is all down to the fact that the compiler builds up this parse tree, and when it has the tree there, it can see the whole of your function. Currently, the interpreter that we have only ever sees one primitive function at a time, so it's limited in how much analysis it can do. We've got an idiom system that recognizes, sometimes sequences of 2 or 3 functions, but that has its own restrictions in that you have to write the idioms exactly in the order that Dyalog thought of them. And there are certain expressions that are not easy to express as an idiom. And again, as was it John or Roger were saying, when we have function trains, that's another way where the existing interpreter can spot combinations of more than one function at a time. But I hope that what we've done with the compiler will make that an order of magnitude better, in that it can see a whole defined function's worth of work at one go and can do analyses on that parse tree. So some of the sorts of analyses that we're thinking of doing. Here's another function from the tradfns workspace, something to do with multi-dimensional spheres. You might notice in the middle here, that says circle 1, which is calculating pi. At the moment, when you run that function, it'll pick up the number 1 and pick up the function circle and go off and calculate pi for you. There's no reason why we shouldn't do that up front at compile time when the function is fixed. We know what pi is. Another simple thing here is that the expression n divided by 2 is used twice. With the current system, it'll never notice that. It will just evaluate it twice. With the compiler, we'd like to be able to spot that when we build up the parse tree. And the second time we get to the divide by 2, we'll say, well, we've already calculated that result. We'll just reuse that. A slight variant on that, once you've got the parse tree, is that you can start inferring properties of the expressions or of the array values that you're calculating. So if you see the number 1 in the code, you know it's a simple scalar, you know it's an integer, you know everything about it. the tally function, when the compiler sees that, it knows that the result of tally is always a simple scalar. So at this point, we know that the plus function will be applied to two simple integer non-negative scalars. So that's opening up the way to call a specialized version of the plus function, because the general plus primitive has to worry about, are the arguments nested, have they got 7 dimensions, are they .NET objects, all that stuff. This allows us to statically infer some information about the arguments. We can call a specialized version of the plus function that says, I know exactly what I've got. I've just got 2 numbers, they're integers. It's very simple. There's no runtime testing left to do at that point. I'm sorry? Bob points out that there is some testing. You have to test whether the result overflowed, and that's true. And getting into implementation details, really the main barrier to going further with this is there's a kind of explosion of complexity, because you can do this for any primitive function. You can say, well, we should have a specialized version of divide for when the left argument's an integer and the right argument's a 2-element vector, or keeping tabs on that complexity and working out exactly which things should be specialized and how to implement it that's why this part is still a research project. And another thing, I mentioned the current idiom system. Currently, I think this sequence here, starting with the open brace, I guess, the sum of the and scan of where the argument is a space gives you the number of leading spaces in a string. But people forget these things. Maybe you wanted to write omega equals space instead of space equals omega. At the moment, the idiom system is not clever enough to cope with that kind of variation. But what we can do, what I have implemented already in this compiler, is it will recognize all your old favorite idioms, but in a more flexible way. So if you start switching the arguments around, it says, sure, okay, as long as you've got an equals on one side as a space and the other side is an omega. And it will work. Okay, so it will work if you swap the arguments. It will work if you've put parentheses in where you didn't really need them. It'll even work if you did omega equals space on one line, assigned that to some local name, and then did the rest of the expression on a separate line. So that part of it is much more flexible than the current idiom system. So hopefully, if you like the sound of this, you're asking, where is it? When can I get it? And as we've been saying, it will be available in a beta form in version 14, but it will be disabled by default, so it won't interrupt the normal running of your programs. If you want to play with it, currently we have the iBeam interface. We also have, I have some ideas about hooking it up to the graphical user interface. That's not really my department, but wouldn't it be nice if you were writing a function in the function editor and there was a little light or something that said, oh, what you've written is pure, I can compile this. And then you do something it doesn't like and a little warning pops up and says, oh no, you're doing this. For the time being, we just have the iBeam interface. And what can you do now to kind of prepare for this technology? Well, as we've been saying all along, thinking in a pure functional way is always good for these kind of compiler technologies, avoiding the use of global names and semi-globals wherever you can, trying to avoid updating global state and things like that. Using dfns is not mandatory, but it's a very good way of encouraging yourself and your colleagues to write code in this kind of way. And we're very open to you showing us code that you have, if you have utility functions in your system that are used a lot, that you think should be compiled or you think we might like to focus on. We've solicited input from some customers at least, and some people have provided us with functions. We can't promise that we'll be able to compile them, but it's all useful stuff to focus our efforts. As I say, there are some things that are simply not implemented yet because we don't have time. Having real life examples from customers would be a great way of focusing our efforts on what we really need to work on. So that, I think, is all I wanted to say. Are there any questions?
Sure, I got a few. It's defunds only right now. Is that correct? Defunds only?
Sorry, where am I looking?
Defunds.
I've got a slide about that. Well done. No, it is not defunds only. We encourage the use of defunds, but I think Morten mentioned that if you write a traditional function which is morally equivalent to the defun way of doing it, so all your names are localized, then it will cope with that just as well as it coped with the defun.
So as long as you're encapsulated, you're going to be okay.
Yes.
You won't have to rewrite it as a defund.
You don't have to, no.
Excellent.
I mean, one slight gotcha is that once you started writing traditional functions, you might feel tempted to use complicated control structures and things like that. We haven't been, because we're focusing on defuns, things like, while loops in traditional functions aren't supported.
Okay. In the example that you showed before, where you had a global call to days,
Yes.
it seems to me a pretty good assumption that the days that your execution time is going to be the days that you compile to. So if you could store the signature or some kind of checksum to make sure that that's true, that your assumption was true, even though there's other possibilities, maybe most of the time you'll be right.
Yes, absolutely. Many people have said that, and you're dead right. We should have systems for, as you say, kind of assuming that days is a function, and maybe just to be sure, when you run it, there's a very quick check just to make sure that it still is a function. It hasn't gone away in the meantime.
And then finally, when you give up, you might
Yes.
give up part way through. In other words, you might be able to do some analysis that's worthwhile storing, and then say, okay, I have to give up at this point, and you might be able to gain that way. I'm just thinking.
Again, other people have asked for that. The only reason for not doing that is it sounds complicated. Maybe we need a clever person to implement that bit. Hello, okay. Diane.
So one of the things that we struggle with is maintaining large workspaces with lots of functions spread through various namespaces. And so what we've tried to do is develop utility namespaces, okay, for those things. So, but what I see here is that the developers are going to be tended to, okay, I'm just going to scatter all these defuns in all of my functions. Okay, now if we find a bug in one of those and it's spread through everywhere, okay, I got to find all those cases of it. So what we'd really like to do is to be able to have all the advantages of the compilation, but have it work from utility namespaces. Okay, so that I call, say your days, okay? Could
Yes.
if I had that as, pound.myutils.days, okay, am I going to get the speed up or not?
Yeah, so the fact that the function days itself lives inside a namespace, that's no problem at all. It can still be compiled. That's absolutely fine. The only tricky bit is when one function calls into another function. And again, that's nothing to do with namespaces. It's a general restriction that we can't have at the moment. We can't have top-level functions calling other top-level functions. So I'm not sure if that answers your question, but if you're only interested in compiling single functions at a time, then the fact that they live in a utility namespace is certainly not a problem.
Okay, but then your example there, the function that called the days, okay, am I going to get the speed up from it?
No, there's a general restriction at the moment that a function that calls something like days itself will not be compiled. But generally, I think it's a good idea to focus most of your optimization efforts on the kind of bottom level functions. That's the hope anyway, functions that do some computation and don't involve calling out to other functions.
Okay, thank you.
One last question.
Okay, so I have to say this is absolutely great work, and I'm hoping that maybe you will be looking at how the JVM has been optimized heavily over the years. Will you be taking any of that and doing runtime optimizations and other stuff?
I'm familiar with an extent to what they do in the JVM, and typically that's to do with spotting which bits of code are being executed a lot, and then spotting that something has been run 100 times already and saying, oh, okay, maybe we ought to go over there and spend a lot of effort recompiling that bit. I think what's possibly more interesting is JavaScript these days. JavaScript is so ubiquitous that a lot of very clever people have put a lot of effort into writing, optimizing JavaScript runtimes like V8 in Chrome, and Firefox has got something equivalent. And because JavaScript is a very, very dynamic language, it has a lot of the same problems as APL. You're never quite sure up front what names are going to refer to. So I'm certainly very interested in the technologies they're using. I can't promise exactly which of their ideas I'll be able to steal.
Okay. So, Jay, thank you very much.
Thank you.